It is my great pleasure to introduce Anton Burkov from the University of Waterloo. He received his PhD from Indiana University. Actually, I should probably say it more correctly. Actually, it is Indiana University in Bloomington in 2002. He had several postdoc positions at the University of California, Santa Barbara with Leon Valance. Then he had a postdoc position at Harvard with Eugene Dallmer, and he joined University of Waterloo in 2007. He is a full professor now, and he worked on wild semimetals, topological insulators. He actually was one of the people who introduced the ideas of wild semimetals before those were discovered. So without any further ado, welcome, Anton, and please, you may start.
Thank you, Igor. Thank you for inviting me. This is certainly a new experience for me. This is my first online colloquium. So let me start actually by asking the following question. If you don't understand where this question is coming from, don't worry, you will understand in a few minutes. The question is, where do gapless excitations come from? Okay. So let me start by talking about a prototypical condensed matter system. So a liquid of interacting bosons, for example, liquid helium. So in this case, the energy of the bosons of the, let's say, helium atoms is just p squared over 2m. And it's natural to count that energy from the value of the chemical potential, mu. And so you know that at high temperatures, chemical potential is going to be large and negative. So this is because chemical potential is a derivative of the free energy with respect to the particle number. And at high temperatures in the classical regime, the entropic contribution to the free energy is going to dominate, minus Ts. And so the chemical potential is going to be negative. So what this means is that basically the energy of the bosonic atoms counted from the chemical potential is going to be large and positive. Okay. And in this sense, at high temperatures in this helium liquid, there are no low energy excitations. Okay. However, if we reduce the temperature, you know that so the magnitude of the chemical potential is going to decrease, and eventually there is a critical temperature where chemical potential hits zero, and this marks a transition to a superfluid state. So the helium liquid becomes superfluid, and when that happens, the excitation spectrum changes drastically. So now we have gapless excitations with linear dispersion, and so the excitations are basically acoustic phonons. Okay, so when the transition happens, excitation spectrum becomes gapless. Now, and as most of you know probably very well, you can understand the origin of this gapless spectrum using the concept of spontaneous symmetry breaking. So you may think about the transition to the superfluid state in terms of the field that creates or annihilates bosons developing an expectation value. And so the phase of that expectation value is arbitrary. And it's this arbitrariness of the phase, which is chosen spontaneously, was what's behind the appearance of this gapless excitation spectrum. Now, something very similar happens if instead of forming superfluid, the atoms actually form a crystal. So crystal breaks translational symmetry of space. And as a result of that, we also have gapless spectrum, which actually has exactly the same form as in the superfluid. So gapless acoustic phonons, whose energy goes to zero in the limit of the wave vector going to zero. So there are a couple of lessons we can draw from these two simple examples. So lesson one is that gapless excitations do not arise accidentally. There must be a reason. So a generic situation is a situation with a gapped excitation spectrum. And lesson two, the existence of these gapless excitations, and that's really why I'm interested in them, their existence is associated with interesting physics, such as superfluidity, crystallinity, and so on and so forth. Now, so this was about bosons. Now, if we think about fermions, and I will really be interested in electrons and solids. So the physics of electrons and solids is really defined by the following three principles. The first one is that the energy spectrum of electrons in solids has the form of bands separated by band gaps where there are no allowed energy values. The second principle is that electrons obey Pauli principle, so no two electrons can occupy the same state. And the third principle is that the number of states in a particular band is always twice the number of unit cells in a crystal, okay? And so as a consequence of that, if you have an even integer number of electrons per unit cell, there's going to be a certain number of completely filled bands and a certain number of completely empty bands, or in other words, the Fermi energy is going to be in the band gap, and the material is going to be an insulator, no gapless excitations. Now, this picture is a little oversimplified, because as you know, the bands can overlap in energy, but let me keep it oversimplified for the sake of the argument. Now, in contrast, if the number of electrons per unit cell is fractional, by which I mean not even integer, okay, then we get a metal. Then the Fermi energy crosses at least one of the bands, and we get a Fermi surface of gapless excitations whose volume, the volume enclosed by the Fermi surface, is directly proportional to the number of electrons per unit cell modulo even integer. So this is a famous theorem by Lessinger. Okay. And so metals, again, by the same reasoning as I used before. So metals having gapless excitations, this actually leads to interesting physics, and also this makes metals useful. So metals conduct electricity well. So we can make wires out of them, right? Metals conduct heat well. That's why we can use them as we can make cookware out of them. Metals are ductile, but also often pretty strong. So we can make various things for that we can use in construction. And metals are also just shiny and beautiful. And all of that, in one way or the other, is connected to the fact that they have gapless excitations. Okay? In contrast, insulators are boring. Okay, so well, again, this is a little bit of an overstatement and oversimplification, but generally, metals are more interesting than insulators. Now, and so recently, and by recently I mean in the last maybe 20, 30 years, we've realized that that actually there is a third way in which gapless excitations can arise. So I've described the spontaneous symmetry breaking and the filling of electrons per unit cell. Now we know that there is also that gapless excitations can also appear for topological reasons. So what we've understood is that insulators are actually not as boring as this picture suggests. And there are in fact two distinct classes of insulators, which are not adiabasically connected to each other. And so one of them is ordinary, which is indeed as boring as this piece of rock, but the other one is topological. And so topological insulators are insulators that are boring in the bulk, that don't have any gapless excitations in the bulk, but which necessarily have a metal, so gapless excitations on their surface. Okay. Now, and so a natural question that follows from this that we can ask is, can actually bulk three-dimensional metals be topologically non-trivial in the same sense as insulators? Or in other words, can I have a bulk three-dimensional topologically protected metal when the material should be an insulator by band filling, namely when I have an even integer number of electrons per unit cell? Okay. Now, again, as you know, bands can actually overlap in energy, and so many materials with even integer number of electrons per unit cell are actually not insulators. They are metals or semimetals, as they're called. However, in this case, it's accidental. So what this means is that at least theoretically, I can change some parameters in the Hamiltonian, and without breaking any symmetries, without really doing anything drastic, I can remove that those gapless excitations and open a gap. Okay, I'm not going to be interested in such an accidental semimetal. I want to know if there can be a metal at even integer band filling that's mandated by topology in the same way as insulators. Okay. And so, indeed, such a situation exists, and this is what's called wild semimetal. Okay, so wild semimetal is a gapless topological phase which arises in 3D materials which lack either time reversal or inversion symmetries. So they are either magnetic or the crystal structure lacks center of inversion. In these materials, bands touch at a certain number of points, which always has to be even, and the Fermi energy coincides with those touching points. Okay, so again, this should be an insulator by band filling, but since there is no band gap, the bands touch, this is actually not an insulator. And it turns out that this kind of situation exists unavoidably as an intermediate phase between topological and ordinary insulator in 3 dimensions, when a direct transition between them is impossible. And that's always the case when there is no time reversal symmetry or inversion symmetry. Okay. Now, actually, the simplest situation in which it arises is when time reversal symmetry is broken. And so there is a transition then between an integer quantum Hall insulator in 3 dimensions and ordinary insulator. So let me explain actually how this works. So suppose I have a very thin film of a 3-dimensional topological insulator. Okay, so in this case, as you know, as I mentioned, there are gapless surface states, let's say on the top and the bottom surface, which have the form of 2-dimensional Dirac fermions, and their gaplessness is protected by the time reversal symmetry. Now, suppose I break time reversal symmetry somehow. For example, I can do that by doping this topological insulator film with magnetic impurities, or I can use actually an intrinsically magnetic topological insulator and just lower the temperature below the critical temperature. So in this case, a gap will be opened in the Dirac surface states on the top and bottom surface. And so you know that I've probably heard that kind of a important feature of the response of a 3-dimensional topological insulator is something that's called parity anomaly. So what it means in this context is that when you gap the Dirac surface states by breaking time reversal symmetry, you actually get a contribution to the Hall conductivity that's half quantized. That's equal to E squared over H, over 2H, okay? So you get E squared over 2H from the top surface, E squared over 2H from the bottom surface. So the total is E squared over H, okay? And so such a thin film is gonna be basically a quantum Hall insulator that has a Hall conductivity of E squared over H. Now, imagine that I make this film so thin that the top and the bottom surface are actually hybridized. And so the delta here is the parameter that describes this hybridization. Then, so what phase this film is going to be in will depend on the ratio between the energy scale that's related to the magnetization. I'm going to call that B. Okay, you can think of this as just the same on energy, and delta. So when B is less than delta, the Hall conductivity will actually be 0. while when B is greater than delta, the Hall conductivity is going to be E squared over H. Okay, and so then as a function of B, you have basically what's called an integer quantum Hall plateau transition. So at when B is equal to delta, the Hall conductivity is going to jump from 0 to E squared over H. So that's a classic integer quantum Hall plateau transition. But now suppose I want to make I want to make a three-dimensional structure out of such thin films. Okay, so I will make a stack of such thin films in the, let's say, the Z direction. Let me call the growth direction of this heterostructure the Z direction. Okay, so D is the period, and I now have two parameters, delta S and delta D. So delta S describes the tunneling amplitude for electrons to tunnel between top and bottom surface in the same layer, while delta D is between neighboring layers. Okay. And so then what's going to happen is the following. So when magnetization is large, what I will have is basically 3D integer quantum Hall effect. So I will have a Hall conductivity of E squared over H per D, per the period of this heterostructure. Okay. And I can write this in terms of a reciprocal lattice vector that corresponds to this superlattice in the Z direction. So E squared over H times G, this reciprocal lattice vector divided by 2 pi. But now suppose I want to now go have the same, go through the same transition as I discussed in 2 dimensions. I want to reduce magnetization and go from sigma xy equal to this to sigma xy equals 0. Okay, and so a major difference from 2 dimensions is that in this case, Hall conductivity is not dimensionless in units of E squared over H. It's proportional to a wave vector, right? And so then, since wave vector can have in principle any value within the first Brillouin zone, right? There is no reason that this transition has to happen as a jump at a single point, okay? So in fact, transition actually must happen smoothly, okay? And it happens precisely through the formation of the wild semimetal phase. So basically, as you reduce magnetization, this band gap closes, okay? So you get a pair of wild points, okay? And the Hall conductivity then is equal to E squared over H times the distance between those 2 wild points in momentum space. And as you reduce magnetization, the wild points smoothly move towards each other and eventually annihilate in the center of the Brillouin zone, and the Hall conductivity becomes equal to 0. Okay. So basically, this sharp plateau transition that we had in 2 dimensions is replaced by this intermediate wild semimetal phase. Okay, and this happens unavoidably, as I said. Now, so there is another way to think about this Hall conductivity of a wild semimetal being proportional to the separation between the wild nodes in momentum space, and this has to do with this phenomenon of chiral anomaly that's well known in particle physics. So basically, the way it works is as follows. Suppose I take my wild semimetal and I apply a magnetic field in the direction in the Z direction, and that's the direction connecting the 2 wild nodes. So then what happens is that this wild semimetal dispersion breaks up into a bunch of Landau levels, which look like this, which disperse in the direction of the magnetic field. However, so it turns out due to the non-trivial topology of this wild semimetal state, there is a special Landau level which connects the 2 wild nodes and which is chiral in the sense that the dispersion has chirality, and that actually reflects the chirality of the wild nodes, the left-handed or right-handed. Okay. In this case, the Hall conductivity may actually be calculated as a derivative of the electron density with respect to the magnetic field. And roughly speaking, this is because, as you can see, due to the existence of this special Landau level here, you have everywhere in between the while nodes an extra Landau level compared to the range of momenta outside of the while nodes. Okay, and so basically you can say that the Hall conductivity is a derivative of the extra Lachenzer volume with respect to the magnetic field, and the extra Lachenzer volume results from the existence of this extra Landau level. So you may think of this special zeroth Landau level as an effective one-dimensional system, okay, whose Fermi momenta, the momenta where the dispersion intersects the Fermi energy, are basically the location of the while nodes. Okay, and so in this sense, there is a nice connection here to the Lachenzer theorem, which I mentioned before. Okay, so the Hall conductivity is just derivative of the Lachenzer theorem for this effective one-dimensional system with respect to the magnetic field, derivative of the Lachenzer volume with respect to the magnetic field. Now, so I can turn this argument around. I can say that a fractional Hall conductivity, and by fractional I simply mean a Hall conductivity which is not proportional to reciprocal lattice vector divided by 2 pi. So that situation I will call the integer 3D Hall conductivity. So a fractional Hall conductivity where there is just a some arbitrary wave vector in the first Brillouin zone in the absence of a Fermi surface inevitably implies the existence of while nodes. Okay. So in this sense, chiral anomaly, the existence of the chiral anomaly, which is manifested in this non-integer fractional Hall conductivity in the absence of a Fermi surface, inevitably implies while nodes. Okay. Now, there is another aspect of the chiral anomaly, which is probably more well known at least in the particle physics context, and this has to do with non-equilibrium phenomena. So, if I look at this while semimetal dispersion, and suppose I move the Fermi energy a little bit away from the while nodes, this will actually happen inevitably. Because there are, in any material, there are always impurities, and so the Fermi energy will always move away from this stoichiometric value. So in this case, I have two pieces of the Fermi surface, each enclosing an individual while node. Okay, and I can say that if in the absence of scattering between the two pieces of the Fermi surface, which is typically is going to be weak if they are separated sufficiently far away in momentum space, the number of electrons under this Fermi surface and this Fermi surface, the left-handed and the right-handed electrons, should be separately conserved. Okay. However, this actually turns out not to be the case, and if I go back to the same picture of Landau levels, it's clear that if I apply now, in addition to the magnetic field, I also apply an electric field in the same direction, in the z direction, then they will actually be pumping of electrons, since the electric field is going to accelerate electrons. They will be pumping of electrons, let's say, from the vicinity of the left-handed node to the vicinity of the right-handed node in momentum space. And so the individual right-handed and the left-handed electron densities are actually not conserved. The total, of course, is conserved. Okay, so this is what's normally called chiral anomaly. But I want to emphasize that there are actually two aspects to the chiral anomaly. This one, the non-equilibrium, and the equilibrium, which is expressed in this Hall conductivity, which is proportional to the separation between the while nodes. Now, and so this effect actually leads to very interesting phenomena. It leads to a drastic modification of the density response in such a metal. So let me remind you briefly how what the density response looks like in an ordinary metal. So in an ordinary metal, you know that the transport of charge is basically described by diffusion equation, and that's a consequence of the conservation of the number of particles. So, well, you all know what diffusion equation looks like. And so on the other hand, since the charge is conserved, this is a continuity equation. So dm dt is equal to minus the divergence of J. And so I can read off immediately from here an expression for the charge current. And so the fact that there are two terms here expresses the two contributions to the charge current. One, the diffusion contribution proportional to the gradient of the density, and the drift contribution proportional to the electric field. And so the diffusion constant and the conductivity are related, as you know, by this Einstein relation. Now, so let's think about what should the density response be in a wire metal, in a topological metal. So, well, naively, now the only difference is that instead of just single conserved quantity, total charge, now I have two conserved quantities. So I can say that I have a total charge that's still conserved, but there is also chiral charge, the difference between the left-handed and the right-handed, that's also conserved, okay? Well, this one is not going to be exactly conserved because there is always going to be some scattering between the two Fermi surfaces, but I can say that it's almost conserved. So that scattering is weak, meaning that the relaxation time associated with the scattering is very, very long, okay? And so if that's the case, then I can write two diffusion equations, one still the same diffusion equation for the total charge, and then the second diffusion equation with a relaxation term for the chiral charge, okay? However, it turns out that this phenomenon of the chiral anomaly actually leads to coupling between those two equations. And so the true equations that determine the density response in a wire metal actually look like this, okay? So I have these usual terms, the quadratic terms and the relaxation, but in addition, there is a term that's proportional to the magnetic field, and that involves only first derivatives, okay? Meaning gradient of the density and gradient of the applied electrostatic potential, which is the electric field, okay? And so this coefficient here is basically magnetic field times some universal constants, and that's a direct consequence of the chiral anomaly. And just by looking at this equation, you can immediately see that, you know, this is going to really lead to a drastic modification of the response because unlike the usual diffusion equation, which involves second derivatives, second spatial gradients, these new terms have first derivatives, and first derivatives will always dominate second derivatives on long enough length scales. Okay, so to see actually quantitatively what happens, what we can do is Fourier transform and diagonalize those equations. So find the eigenmodes, right? And so this is an elementary exercise, and this is what you find. So there are two modes, okay? So I have I omega equals some function of Q. So if the right-hand side is real, then this describes an eigenmode with an imaginary frequency. That's a diffusion mode. This describes a purely relaxational dynamics, like an ordinary metal. And so this is indeed the case when the wave vector is small enough, right? So when the square root is real, then I basically get two. So in the limit when Q is small, I get basically two diffusion modes. One, the usual diffusion mode, I omega equals dq squared, and the other one, dq squared plus the relaxation rate, and this corresponds to basically decoupled diffusion of the total charge and the chiral charge. Okay. However, so you can see from this expression that when Q is large enough, right, basically when Q is greater than this, this quantity here, then the square root becomes imaginary, and what that means is that I get a propagating mode. Okay, so the solution looks like omega equals this coefficient gamma, which is proportional to the magnetic field, times Q, so a linearly dispersing sound-like mode, okay, whose velocity is proportional to the magnetic field, and then a diffusive relaxation term. And so as long as Q is small enough that this term dominates the relaxation term, I actually get a propagating mode, okay? And so these two conditions, Q greater than this, and Q basically is small enough that the first term dominates the relaxation term, gives me a range of the wave vectors in which I have a propagating mode. Okay, so I can write this in terms of these two length scales, L star, which is related to the chiral charge diffusion length, and LA is directly related to the magnetic field. Basically, LA is inversely proportional to the magnetic field. Okay?
Anton?
Yeah.
There is a question from the audience, if it's okay to ask now.
Sure.
Masoud, go ahead.
Hi. I wanted to ask that in your diffusion equation, you used the Ohm current. You added the Ohm current, I guess.
Yeah. So there is I've added electrostatic potentials, but that's mostly just to the V, the electrostatic potential V, that gradient of V is just the electric field, the applied electric field. Now VC, so the potential that couples to the chiral charge, that's just a kind of technical device that allows me to calculate a response function.
I wanted to ask that could we also add current, like a chiral magnetic current here?
Well, I will actually talk about this, right? So
thanks.
I can deduce the existence of a new contribution to current from this equation, but this is coming, okay?
Thanks.
Okay, so so I have these two length scales, and the inverse of the two length scales define a range of wave vectors in which a propagating mode exists. And so the existence of this is really unusual if you think about this, right? So in an ordinary metal, you always get diffusion. So the charge dynamics is purely relaxational, right? So if you create a charge disturbance, it's gonna relax according to diffusion equation. But in a topological metal in magnetic field, you actually get, there is a regime in which you get propagating modes, okay? And this exists even in weak magnetic fields, and when there are lots of impurities, right? And so this is really a qualitatively new feature of topological metals, the existence of such propagating modes. Now, okay, so the question is, how do we observe this? What are the observable manifestation of that? And one of them, so there are actually observable manifestations that can be seen even in DC transport, okay? So one way to see this is the following. So let me take the second equation, the first equation, the equation for the total electric charge. So since the total electric charge is strictly conserved, right? The right-hand side of this equation has to have the form of minus divergence of the current. And therefore, just as before, I can read off an expression for the electric current from this expression, just remove basically one derivative. And so what this gives me is that in addition to the Ohm's law contribution to the current, right, sigma times the gradient of the electrochemical potential, or sigma times the electric field, I get in the topological metal in magnetic field, I get an additional contribution to the current that's proportional to this coefficient gamma, which is proportional in turn to the magnetic field. and also to mu c. And so mu c is the chiral electrochemical potential. What that means is that this is the difference between the chemical potentials of the right-handed and the left-handed electrons. Okay. Now, so this contribution is very unusual, and so what's unusual about that is the following. So let's think about the two contributions to current, the ohmic and this one, in terms of symmetries, right? So we know that current is odd under time reversal symmetry, right? Because it's if you reverse the time, you reverse the momenta of the electrons. So this reverses the direction of the current. However, chemical potential and gradient of the chemical potential is certainly even under time reversal. So that seems strange. How can a quantity that's odd under time reversal can be proportional to the quantity that's even under time reversal, right? And the answer is that the sigma here, the conductivity, the process by which this conduction happens involves irreversible randomization of momentum. And so it means it's dissipated, right? And so it's reflected in this usual Drude expression for the conductivity by the fact that it's proportional to the scattering time tau, right? So that's basically the mean, the average time between collisions of electrons with impurities. And so this process is dissipative, and therefore we shouldn't really expect time reversal symmetry, right? However, this second term here, the coefficient, the mu c, is still even under time reversal, but gamma is odd, right? So both J and gamma are odd under time reversal. What this means really is that the second term describes a contribution to transport that's non-dissipative, right? And this is in some sense similar to what you get on superconductors, right? If you recall London equation, in superconductors, the relation between the current and the vector potential, it has the same property, right? So both the current and the vector potential are odd under time reversal, and this expresses the fact that the supercurrent in a superconductor is non-dissipative, okay? So, and so this effect, and so this extra contribution to the current proportional to the magnetic field and chiral electrochemical potential is called chiral magnetic effect. So chiral magnetic effect is a new channel of conduction that exists in topological metals that's non-dissipative, and that's very interesting and potentially useful. Okay. Now, okay, so how does this actually manifest? So what this manifests in is a phenomenon that's called anisotropic magnetoresistance. Okay, so basically, if you have, let's say, this is my sample, and I have a current flowing in the x direction, and so suppose I have magnetic field that's applied actually at some angle in the plane of the sample, but at some angle theta to the current. Okay, so then it turns out that if you measure the resistivity tensor in this system, the longitudinal resistivity rho xx and rho yx, they look like this. Okay, so there is a negative contribution to the resistivity that's going to be proportional to delta rho, which in turn is related to this to the magnetic field. Okay, it's actually going to be quadratic in the magnetic field, and there is also an off-diagonal contribution to the resistivity rho yx, which is called planar Hall effect. It's not really Hall effect. It has nothing to do with the Lorentz force. It just arises basically because the resistivity along the field and perpendicular to the field is different. Okay. Now, so in principle, anisotropic magnetoresistance is a well-known phenomenon. It exists in all ferromagnets, for example. And in this case, basically what it depends on is the angle between the current and the magnetization. Okay. However, in ferromagnets, first of all, this requires magnetization, okay? And it also is typically very small. So one can characterize this effect by, let's say, the ratio of this correction to the resistivity by the resistivity in zero field. And the largest anisotropic magnetic resistance that I could find in the literature is in this exotic heavy metal ferromagnet, uranium arsenide, and it's 50%, okay? So in topological metals, this effect can exist without any magnetization, okay? It has to do with it's related to the angle between the current and the magnetic field, right? And the magnitude can be very, very large. In fact, even in current materials, which are far from perfect, you can see an isotropic magnetic resistance of several 100%, okay? So seen, for example, in this material, sodium-3 bismuth. So this is potentially useful technologically. Now, so in addition to DC effects in the form of this anisotropic magnetic resistance, there are also dynamical effects that can be seen in the optical conductivity. So basically, this density response, which I've discussed, can be related from charge conservation to conductivity by this formula. And what you get then is the following phenomenon. So you know that in metals, the frequency dependence of the conductivity has the form of this Drude peak, right? And so the width of this peak is directly related to this time tau, which describes the scattering of electrons on impurities, okay? So it turns out that in a topological metal, once you turn on a magnetic field, so this new new conduction channel turns on, and this new conduction channel manifests in an extra peak, which grows on top of the Drude peak, okay? And whose width is proportional to the chirality relaxation rate, 1 over tau c, instead of the momentum relaxation rate 1 over tau. And since tau c is going to typically be very large, much larger than the momentum relaxation rate, there's going to be a narrow peak in the optical conductivity whose width, again, is proportional to 1 over tau c, and the height is proportional to square of the magnetic field, okay? So this this effect may have been seen already, although I mean it doesn't look quite as spectacular as my picture here, but it may have been seen in cadmium arsenide. That's another topological semimetal material. Okay, so let me very briefly also talk about some effects that arise as a result of interactions, okay? So far, what I've been talking about is purely non-interacting physics. Basically, you can say Landau Fermi liquid physics of topological metals. Now, one can also ask, do you also get potentially interesting phenomena if there are strong interactions, okay? And the question you can ask here is the following. So this, as I've described, the chiral anomaly in the form of this fractional Hall conductivity proportional to the, not to a reciprocal lattice vector, but to separation between the Weyl nodes, inevitably implies Weyl nodes in the case of non-interacting or weakly interacting electrons. We can ask the question, does this remain true when the interactions are not weak? In other words, I can ask, can I gap out Weyl nodes while preserving the same value of the Hall conductivity, okay? And while not breaking any symmetry. So why is this not breaking any symmetry? It's important because I can always gap out Weyl nodes by breaking translational symmetry, by creating charge density wave whose wave vector is precisely the separation between the Weyl nodes, okay? but that just will give me an integer quantum Hall insulator with a new reciprocal lattice vector, which is equal to the old separation between the Weyl nodes. So the question is, can I gap out Weyl nodes without creating this charge density wave? Okay. And it turns out that the answer is yes, and the state that you get by doing that is actually very interesting. So the state is a generalization of the fractional quantum Hall effect, but to 3 dimensions. Okay, so basically the answer is that we can defeat this chiral anomaly, but at the cost of fractionalizing electrons and creating topological order. Okay, so I'm not going to be able to describe this in detail. Let me just very briefly talk about how this can be established. So basically, the procedure is the following. So what we do is I imagine we induce a superconductivity in Weyl semimetal, which gaps Weyl nodes. Okay. And then we imagine destroying superconducting coherence by condensing vortices while keeping the pairing gap. Okay, so if I condense vortices in a superconductor, this destroys the superconducting coherence. But since I keep the pairing gap, there are no low energy fermion excitations, and therefore what I get is an insulator. Okay, so what I imagine doing is basically inducing a superconductor to insulator transition in the Weyl semimetal, in the superconducting Weyl semimetal. And it turns out that that chiral anomaly places very strong restrictions on this procedure and prohibits a simple insulator, but allows an insulator that has topological order, and which is basically a generalization of the 3-dimensional fractional quantum Hall effect to 3 dimensions. Okay, so well, let me actually skip all of that. Let me actually go right to the result. So basically what we predict is the following, that so in a non-interacting or weakly interacting Weyl semimetal, I have the following picture, right? So as I change the magnetization, I'm going to have this smooth transition from an ordinary insulator with sigma xy equals 0 to an integer quantum Hall insulator with sigma xy proportional to the reciprocal lattice vector. So with strong interactions, we predict that there can be a plateau in this smooth dependence where the Hall conductivity is quantized to exactly half this value, to exactly half this integer value. Okay, and so this is an exact analog of a 2-dimensional fractional quantum Hall state. So in that case, in 2 dimensions, if you just have let's say a 2-dimensional electron gas in the magnetic field, you get plateaus as a function of the magnetic field when you change the Landau level filling. The analog of that here is we change magnetization, okay? And we change the separation between the Weyl nodes, and at certain separations, basically when the separation is exactly half the Brillouin zone size, the Weyl nodes can be gapped without breaking any symmetries, and you get a half quantized plateau in the Hall conductivity. Okay, so again, if you are, I had to skip the details because this would take me a long time to explain. If you are interested in details, please read this paper. Okay. Okay, so I guess at this point, let me conclude. So what I've shown is that both insulators and metals may be topological. So basically in 3 dimensions, in materials which break either time reversal or inversion symmetry, we can get a metal when band filling actually says that it should be an insulator, right? When band filling is an even integer number of electrons per unit cell. So this topological metal is a metal whose Fermi surface breaks up into disconnected sheets, each enclosing a while node, which acts basically as a magnetic monopole in momentum space. So these nodes are topological objects and they lead to observable phenomena. So there are something that I didn't mention, Fermi arc surface states, which connect the projection of the while nodes on the surface brilliant zone. There is giant anisotropic magnetic resistance, which I talked about, and a new dissipationless conduction channel, non-Drude optical conductivity with an extra peak on top of the Drude peak, whose width is proportional to the chirality relaxation rate and height proportional to the square of the magnetic field. And also in topological metals with strong interactions, there can be very exotic phenomena like three-dimensional generalization of the fractional quantum Hall effect. Okay, thank you.
Well, thank you for the very nice presentation. It seems we have plenty of questions coming in the chat, so let me make sure I'll go in the right order. Seems Srimayi, Sri, you were the first. Go ahead.
Yeah, so my question is this fractional Hall quantum conductivity that you're talking about, is this in a two spatial dimensional sample that I can think about it? For example,
no. So it's really three-dimensional. So there is no external magnetic field here. There is magnetization, right? So you can call this fractional quantum anomalous Hall effect in this sense, right? And it really exists in a three-dimensional sample. So what you need is just to gap out while nodes. So if you gap out while nodes, you create an insulator, okay? But that insulator actually has a fractionally quantized Hall conductivity.
So if the sample is three-dimensional, usually when I think of Hall effect, I always think of a two-dimensional system, right?
Well, I mean, you can have Hall effect in 3 dimensions just as well, right?
So can you describe the geometry a little bit, like where, in what direction you have magnetic field and in what direction you have
so let's say I have a magnetization in the z direction. There is no magnetic field. There is magnetization in the z direction, yes. And I'm measuring sigma xy. Okay, sigma xy. So sigma in the Hall conductivity in the plane that's perpendicular to the direction of the magnetization.
I see. Okay. And do you have edge modes? Just like
yes. In this fractional quantum Hall state, you mean?
So what kind of edge modes do you have? So
right. So the edge modes are actually pretty complicated. So in fact, this state here is an analog of is a three-dimensional analog of non-abelian fractional quantum Hall state in 2 dimensions. Okay. So there are several edge modes. But so one of them is in fact Majorana, is a chiral Majorana mode.
Oh, okay. Okay, I see. All right.
So there are 3 modes basically. There is a chiral Majorana mode, which carries the thermal Hall conductivity. Okay. And then there are 2 other modes which are counter-propagating. One of them is charged, one of them is neutral. And so those 2 counter-propagating modes carry no heat. The heat is carried by the Majorana mode entirely, while the charge part of the Hall conductivity is carried by one of those non-Majorana charged modes.
So this is described in your 2020 paper?
Yes, that's right.
Okay.
Yeah.
All right, thank you very much.
Okay, let's move on to the next. We have actually a lot of questions, so Masood, please.
Thanks. I want to ask about the physics. I mean, very simple explanation of the anomalous Hall current, because I think that the same effective Lagrangian that can produce the chiral magnetic conductivity for quark plasma can also produce an anomalous Hall current.
That's
but
right. Yes.
I cannot understand its physics. I actually can derive that, but I cannot understand.
I mean, probably the simplest way to think about the physics is in terms of the age modes. Okay, so this is I didn't mention that in the talk, but so basically these materials have what's called Fermi arc surface states. What it means is that there are surface states which exist in between the projection of the wire points on the surface brilliant zone. And those modes are actually chiral in one of the directions, okay? So basically you can think of the Fermi arcs as like a chiral sheet whose extent in momentum space is equal to the separation between the wire points, okay? And each value of them, so if you take a cross section of the Fermi arc, perpendicular cross section of the Fermi arc, each such momentum point, there is a one-dimensional chiral mode which contributes E squared over H to the whole conductivity. So when you integrate that over the whole extent of the Fermi arc, that gives you E squared over H times the distance between the wire points divided by 2 pi. Okay. So it's basically just in this sense, a generalization of two-dimensional Hall effect.
Thank you.
Dimensional quantum Hall effect.
Okay, next is Sergey Moroz, please.
So Anton, I have 2 questions.
Mm-hmm.
So my first question is about AC conductivity.
Mm-hmm.
So usually in the absence of magnetic field, there is an F-sum rule, which, you know.
That's a very good question. Right. So
my question is, like, now you have a magnetic field, do you still have some kind of F-sum rule for
That's right. So of course the total spectral weight under this curve is conserved, right? So this peak is due to spectral weight transfer from high frequencies to low frequencies. So the total spectral weight, this is the equation, right? So the integrated spectral weight is independent of the magnetic field, and it's equal to this. Yeah.
I see. Okay. So this makes it clear. And the other question I have is actually about this, fractional quantum Hall, which you were talking briefly in the end. So in this first step of how to achieve it, you were saying you need to have a superconductor for this.
That's right.
So like if it's really a semi-metal and it does not have any like Fermi surface, so how do you induce superconductivity?
Right. So, you know, it's not, first of all, this procedure is purely theoretical, right? Just a way to arrive at the final result, right? We imagine that the actual quantum Hall insulator is produced by repulsive interactions, right? Not by attractive interactions, of course. So the superconductivity, it's not the weak coupling metallic superconductivity where you get a Fermi surface instability, right? So here you're right that the density of states at the wire nodes is 0. So you have to have a finite strength of the attractive interaction in order to produce a superconducting state. That's fine. Again, this procedure is just a theoretical procedure. It's not that we really think about a superconductor and then how proliferate vortices in that superconductor. This is simply a theoretical way for us to get this strongly coupled insulator. Strongly interaction insulator.
Okay, thank you very much, Anton.
Okay, next is Efrain, please.
Yes, my question is regarding the role of the zero-Landau level in your system, because in similar systems in finite density QCD, we know that the lowest Landau level play a very important role, a fundamental role for the non-trivial topology.
That's right. It's the same here. So, you know, in fact, if you look at these equations here, this contribution here, right, that's proportional to the magnetic field, is entirely due to the lowest Landau level.
I see.
The interesting thing is that even when the Fermi energy is finite, like here, so meaning even when I have many Landau levels on field, the contribution of this single zeroth Landau level is still not lost. Okay, it's still not infinitesimally small, but at long enough length scales, it will always dominate.
Then when you are talking about superconductivity, it will be like a second kind, or because you need the magnetic field to penetrate.
Well, again, so the superconductivity that I talk about here is that's purely a theoretical device that allows me to get an insulator, right? So when I talk about the vortices, I guess I don't imagine, you know, turning on magnetic field and inducing a certain density of vortices and then making them move. What I imagine is that I have an equal so in a superconductor, in the ground state, there are no vortices, right? Vortices are gapped. But then you can induce fluctuations when you have a certain number of vortices and anti-vortices, which are equal, right? And when the fluctuations are strong enough, basically those vortices will condense. Okay, but I have an equal density of vortices and anti-vortices, kind of like Kosterlitz-Thouless transition.
Okay, thank you.
So you don't need magnetic field here, in other words.
Okay.
Okay, I do have a question myself also. When you were talking about the implications of this Chiral anomaly, you talked about this conductivity and isotropic magnetoresistivity. That is kind of very standard thing. However, when you mentioned the chiral magnetic wave, essentially discussing the propagation of that mode looking like a sound, I believe there is one very, very important gap in the logic there. One of the important things that we found recently was actually because of the electrical conductivity, dynamical electromagnetism is extremely important. It kills that mode. In fact, it may survive only in the ultra quantum limit only.
Right. So, you know, which is why I didn't really talk about, you know, detecting this mode directly. Okay.
Okay.
I talked about really these two phenomena, the chiral magnetic effect and the extra peak in the optical conductivity. These are sort of indirect manifestations of the existence of that mode, but it's not sort of measuring that mode directly.
Right.
So, right.
That's true.
That if you actually try to observe that mode, that may be challenging.
Well, what I'm trying to claim is actually bigger than that. I'm saying it doesn't exist. It becomes a real plasmon, unless you go in the ultra quantum limit.
Sure, sure. But you know, this is not going to affect the existence of the chiral magnetic effect and that peak in the optical conductivity, because that has to do just with the fact that there is an extra conduction channel.
Agreed.
That opens up in a magnetic field.
Yeah, that's sure. Yeah, agreed. Other questions? It seems we ran out of questions. I would like to thank Anton again. It was an excellent presentation.
Thank you, Igor.
I'll try to post the video recording for those who missed it or those who want to review it, and I'll send you the announcements where it will be found. So if there are no other last-minute questions, we will be ending up soon. So once again, thank you, everybody. And most importantly, thanks, Anton.
Thank you.